thought I'd just start by saying a little bit about the area. So I work in a part of computer science called natural language processing. So you can think of it as the part of computer science where computer science and linguistics and language meet. To give you some concrete examples, it's also the part of computer science responsible for machine translation, such as Google Translate, and speech recognition, such as Siri, Alexa, and so on. Today, I'm going to talk about grammatical error correction, and I think it's fairly intuitive, but just so you know exactly what it is, here is an input ungrammatical sentence. Grammatical error detection is the aim of finding the erroneous words in the text, and grammatical error correction is the task of then correcting them. Today, I'm just going to talk about several of the various approaches you can apply to tackle this problem. Before I do that, however, it's useful to give you some background on some NLP tools. So when we work with text, you often just start with a sentence, but actually there's a lot of hidden information in this, so we do some additional processing to extract additional information. So the first step is tokenization, which involves simply splitting the text into words or tokens. In English, this is fairly easy because you just split on white space, but in languages such as Chinese, where you don't have white space, it's a lot harder to work out where words end and where they begin. So that's the first step. The next step you can do is you can also lemmatize. So by lemmatize, we mean you convert any morphologically, or the word form is simplified to the form you'd find in a dictionary. So here you've got chickens is plural, and now you find chicken, and R is third person, so you change it to B. Another thing you can do is add part of speech tags. So this just simply says, well, this is a determiner, this is a noun, this is a verb. You can also do more fine-grained analysis. So here NNS is a plural noun, whilst NN is a singular noun. And then something else you can do is parse it, which just finds the structure between all the words in the sentence. So all of this is obtained automatically, and it just means we can go from the start to a lot finer, a lot richer representation of the input sentences. And then this then is useful in downstream tasks.
What's DOBJ?
Direct object.
Okay.
Direct objects, yes.
What's the indirect object?
IOBJ.
No, I mean, what's the difference?
Indirect object would be, I gave a book to someone. Whereas the object is, the giving is the book, and it's the someone is the indirect object.
Ah, I see.
Okay, yeah, feel free to interrupt with questions. So to start off, we'll go very easy, rule-based methods. So subject-verb agreement is probably the most well-known error type, which simply means if you have a singular noun or singular subject, you must have a singular verb, and if you have a plural subject, you must have a plural verb. So chicken crosses and chickens cross, but you can't have any of the other combinations. To fix this automatically, the first step would be to find the subject, which, as you saw from the parse on the previous one, you can use dependency parsing to find. Then you can look at the part of speech tags. So singular noun must go with this form of the verb, the VBZ, and plural of the verb, so plural nouns must go with plural present tense verbs. All other combinations are errors. So if you detect them, you can then fix them by generating the correct form for whichever word you're trying to fix. This is slightly ambiguous because you could ask, well, is it the noun that's wrong or the verb that's wrong? And then you could fix it two different ways. So that's an open question, really. Nice and simple. I'm sure rules are okay. So advantages are it's simple. Another benefit of rules is that they're normally quite precise, because if humans are thinking about it, then, I mean, you're targeting something specifically, so you just make it work, basically. You also only need minimal data, so you don't need any training data really at all. You can just sit down and write these things. One problem is rules can't handle every error type. So here we've got an example of strong computer. It's really hard to write a rule to go, we should change strong to powerful in front of computer. Well, that's such a specific rule that it's not really going to be feasible to do. And And as the more rules you have, of course, the harder it is to maintain, and rules get increasingly complicated, and it just becomes a mess. To show an example of rules becoming a mess, so here is our simple example with fixing subject-verb agreement in the simplest case. You then also have to account for auxiliary verbs, because it's not always the case that the main verb takes the ending that agrees with the subject, so you have to then account for that, which you can do with the arcs here. Then you have things with conjunctions, so whenever you link, so you've got two singular nouns, but when you combine two singular nouns you often get a plural verb, so you don't have to follow the paths that way. Similarly, you can also combine verbs with and again then you need to make sure that both of them agree with the subject. And then you have problems with relative pronouns. So here, which is the subject of hate, but you have to work out then that which also refers back to chicken before you know the form of the verb to agree with. So rules get incredibly complicated very quickly, so aren't really feasible as a long-term strategy. And then there are other exceptions. So nouns don't have to be subjects. You can also have, so crossing the road, that is not a noun, that's just an event, and that's normally singular. And then you have exception nouns like police, which even though it looks like a singular noun, actually takes a plural, the police are doing something. And then other exception, the other way around, £5 are a lot of money, no, pounds is plural, but actually you want a singular verb. So there are lots of exceptions, and this is supposedly the simplest error type, so you can see it probably goes a bit crazy if you do things. Yeah. So, second one, language models. This time I get to ask you a question. Which of these is best?
What?
Yep. And why? Well, it's kind of a hard question to answer. So it sounds better. So, what
number 3?
3 is also okay. So, well, if you had to rank them, would you be able to rank them from best to worst?
Yeah, I'm going to put number 3 as number 1.
Okay, you can do that. Yeah.
Number 2's fine too.
Yeah.
Number 2 also makes
That's
sense.
the line down.
Yes, yeah. So,
Yeah.
yeah. So what you've done is basically applied probability to sentences, where one is obviously you're not ever going to see the. It's very improbable. Whereas I'd hopefully say the bottom one is the most probable, but it is still possible for chickens to cross lines, so it's not entirely impossible, but there is something could happen there. So we basically use this property to detect improbable sequences. And how do we do that? So until recently we used things called n-gram models, where you simply just take a window of size n of all the words in the sentence. So here's n from 1 to 4. There is a trade-off with this, so if you have low n, then you have a high frequency of words, but a very small context, whereas conversely, if you have a high n, then your context is a lot larger, but you'll find fewer instances of this sequence. You then just calculate the probability of those sequences in a large corpus, so a large load of text, and to show how you would then calculate a sentence probability, this is the case of n equals 2, so you have the probability of y being at the start of the sentence followed by the probability of did given y, and the given did, and so on, and you can just calculate an overall sentence probability. How do we use this in error correction? So the first thing you do is you train a model on a large amount of text, so you can download all of English Wikipedia and train on that, and that's a reasonable model of how English works. And then, so that gives you the model, but then you also want to generate a confusion set. So here I've given the example of prepositions, so you just list all the possible prepositions potentially, and then given your sentence you can just try them sequentially. So I often work in home is not very probable, but I often work at home or from home is more probable, and so then you can detect which prepositions are more likely in a given context. And that's roughly how language models work. One of the benefits are you only need native data, so Wikipedia is available, you don't need anyone to annotate anything, so that's nice and easy. Easy to implement, Compared with rules, another benefit is you can detect all error types, particularly collocation errors. So language models you can potentially fix strong to powerful computer because you're unlikely to see strong computer, but you're more likely to see powerful computer. So if you can generate the confusion set, then you can fix it. Language models are also very versatile, so most of the state-of-the-art systems will always include a language model in some capacity. They'll probably have another approach as well, but language models are really good at sort of ranking best, so ranking the best alternatives. So it's a useful tool to have. Disadvantages: probability is not grammaticality. So there was a joke in a book when I was a lot younger. The student begins "I is." The teacher goes, "No, you must always say I am." So the student goes, "Okay, I am the 9th letter of the alphabet." One of the very few occasions where I is actually the acceptable answer. So another case is, so another problem with this is, here I've got the scores for I am at home versus I was at home. And it turns out, based on the data we've used, I was at home is more probable than I am at home, which means potentially your system is always going to make it past tense, even if you genuinely wanted to say you're presently at home in the present tense. So there are issues there. Another problem is rare or unseen words. So paraclassithron is my favourite completely useless word that you'll never ever see ever
What
again.
is that?
So it describes a very specific type of poetry. Imagine the following situation: it's about 3 a.m, you're slightly drunk, you're standing outside your lover's house and no one's letting you inside. That's what that word describes.
It's actually crying next to the door.
Yeah, okay, there you go, cry next to the door. See, we've got Greek confirmation. There you go. Yeah. We've also got Colfefe, which was President Trump's main contribution to the world so far from May earlier this year. So these words will never appear in the language model, which just means it doesn't really know what to do in terms of context. So that's another problem. Another problem is long-range dependencies. So if you only look at short windows, you will potentially see, oh, the Windows is new. That's definitely wrong. And then you work out that actually it's part of a much longer sentence where the house on the corner with the blue windows is new.
Oh,
so
tricky.
But if you had an N that large, then you'd only ever see that sentence once, so you can't really build any reliable statistics from it. So there are pros and cons to language models. So next option we've got is classifiers. So in classifiers, you're basically trying to predict a label given some features. So in this case, I've taken predicting the form of a verb. So you can collapse that down into these 6 labels here. So these are part of speech tags, and these correspond to all the different forms that verbs can have. So I've given the example here of eat. You could also substitute, so the infinitive of be is be, the past tense of be is was or were, the ing is being, and so on. So the goal here would be to predict, so given a verb in a sentence, predict the appropriate label for it. So here, even though eaten matches to VBN, we actually want to predict VBG because we want the ing form, they were eating, not they were eaten. And as I said, we do that with features. So instead of defining rules, you just go, well, what information does a human think will be useful to solve this task? And so here are some sample features. You might just go, is this an auxiliary verb, yes or no? Is this the first auxiliary? Is there an infinitival to? Whatever. Any information that you think would be useful, you can just throw it in, and then you have your gold label at the end. So in this case, I filled it in for were. These would be the values you would get if you filled in the answers as opposed to the questions. And the goal would be, given this yes, yes, no, no, be, etc., predict VBD. And you do that with machine learning. There are all sorts of algorithms you can use. I've shown an example of decision trees here simply because it's easier to visualize. The machine learning algorithm has learned that perhaps this is the best order or the best hierarchy for the questions to solve the problem. And so whenever you see any new data, you just start at the top, answering the yes and no questions, and eventually it'll predict you a label. And that's all we do with classifiers. The main pro is it's more flexible than rules, so you don't actually have to specify if A goes to B then C. You just go, I think A is useful, B is useful, C is useful, machine learning, work out what the best answer is. So it still incorporates the human intuition that rules does, but it's a bit more flexible. Disadvantages are, again, so feature engineering can be complicated. You saw how rules can get really complicated. Again, it can get really complicated to work out which features or which information we need to solve the problem. So smaller confusion sets just means when you predict something, if there are a smaller number of options, your machine learning classifier is going to do better. Whereas if you have to make it choose between lots and lots of options, it's more likely to go wrong somewhere, simply because the number of options is larger than if you had a smaller number of words in your set. So another disadvantage is, like rules, it only targets single error types. So in theory, you have to build lots of classifiers for all the different types of things you want to fix, which isn't really ideal. Here's the Greek I told you about. So the first version of this talk was given in Greece, so I have an example from Greek to English. So another way to think about error correction is as a translation problem from bad to good English. So this just means we can use all the techniques that have been developed for machine translation and apply it to this problem. The first thing you need to know about that is you need parallel data for that. So up until now, you can just use grammatically correct English and just use it to predict stuff. But now we actually need people to manually annotate. This is the original bad sentence, and this is the correct sentence. So we now need to work out how to map the former to the latter. At Cambridge, we're lucky because we have access to the CLC, which is the Cambridge Learner Corpus, which is definitely the largest corpus of corrected text. It is private, so only we can use it, unfortunately. But there are a couple of other versions of alternative corpora available, so there is other data sources. It should be noted that this is actually 29 million might sound a lot, but this is actually quite small. So for comparison, there is a single commonly used machine translation corpus that is 500 million words. And generally, the more data you have...
Is that just one language?
No, it's multiple languages, 20 languages.
Okay.
So we don't really have much data for this problem, and more data would definitely help. There are also questions about annotating quality. So Lang 8 was just a web forum, which means it wasn't really strictly professionally annotated. It was literally just people coming online going, oh, I've seen you've written this, I'm going to correct it for you. So there's varying degrees of quality as how well they've done. Another question is proficiency levels. So there are all sorts of different levels of English, and the one you might be working on might not be appropriate to what you're trying to predict. So if you're predicting like very beginner English on a corpus of fairly advanced English, it's not going to work that well. Similarly, genre is another topic. So NUCL, the National University of Singapore Corpus of Learner English, all their essays are about things like how technology affects the modern world and what to do about like IVF treatment, that sort of stuff. So it's quite advanced English, and that's not going to be very useful if you're trying to test on, I went to the beach on Thursday, I had a good time, sort of level stuff. So genre and domain is another problem. How does this work? So I said before, you have the sentence pairs. Again, machine learning solves the problem. So phrase-based SMT just learns the mapping between phrases in the source and phrases in the target. So as examples, so here's the Greek example. However you say that maps to my book, but the others, so discuss about is always wrong, so you would normally map that to discuss, and similarly information goes to information, and so on. And so you just build up a huge table of all the possibilities of what phrases can map to other phrases, and this is stored in the phrase table. So to give you an example of what that might look like, here's the input sentence. Let's discuss about this information, and maybe we've learned this as a phrase table. So these are sort of all the possible ways, potentially, of mapping, there's probably more, of mapping separate sequences to other sequences. And so the goal here is we just want to go from one side to the other and produce a translation of the input sentence. So for example, you could pick that as a possibility, which is hopefully wrong according to the system, or ideally you would pick something like that, or even that. So there are multiple options, and that's machine translation in a nutshell. The main advantage of that is that it can detect all error types at once. All the previous methods only focus on fairly specific types. Another advantage is you don't need any expert knowledge or feature engineering. You can just go, here is some starting text and here is some corrected text. Go work out how to transform the former to the latter. Disadvantages are, depending on how big your model gets, it can take several days to train these things.
That's totally fine.
That's
In other fields, you take years.
okay. That's okay. The neural models also take. You can use increasingly neural translation is happening. That's still only a couple of weeks training, so not years, but yeah. The disadvantage is you need a lot of parallel data, which we just don't really have at the moment. So we can use the data we have and we do reasonably well, but with more data it could definitely be better. Another problem with machine translation is you can have out of vocabulary words. So this is similar to what I said before with paraclassifron, where you're not going to see that in your training data. So the machine translation system is just going to go, what's that? And probably just output it again. Another thing is these models are typically hard to customize in that once you've trained the model, you can look at the output and go, oh, it's doing this wrong. You can't really go back and go, oh, how do I fix this? It's like an inherent part of the model. There's no sort of easy way to go, oh, I should fix this parameter here. It's just the model has learned this. There's not really anything you can do about it. Well, that's more or less what I was going to tell you. So some of the several approaches. I also realized I hadn't given you any numbers for how well these things work. So these are the scores in terms of precision and recall. So precision is out of everything that the system does, how much does it get right, whereas recall is a measure of how much stuff it missed. So what this means is, in terms of detection, the system only detected 30% of all the errors in the data and only got 70% of them right. So, and the problem gets worse if you look at correction, because it's a lot harder to then predict the correct word. So you can see we're still quite a long way from doing amazingly. So if any of you use Grammarly or any other stuff like that to correct stuff, then I would be very skeptical about how good it is. And that's pretty much what I have.